Parabolicity condition depend on P?
Yeah, thank you. First of all, I would like to thank the organizers for the kind invitation and the possibility to present some of the work. As you can see, co-author of this work is one of the organizers, but that was my choice. So I will recall what the stochastic parabolicity condition is, and I will study this condition a bit. Before I introduce this condition, let me say some things about the variational approach to SPDEs. So, this is a typo, I think. For the variational approach to PDEs, one usually has these three sets of Hilbert spaces. I will not use that later on, but it's just to set up something. So the A will map like this. It may depend on T, on omega, and it may be nonlinear. And here the B similar, but it may not map to V prime. It should map to H. And W is usually something like a cylindrical Brownian motion. Now, for such equations, and again, this 2 should not be here. That was a typo. For such equations, you need something to get well-poseness. And the thing that's usually in the literature is a condition like this. There should exist a constant C1, C2, alpha, and there should exist a function which is adapted, such that you have this estimate. And when do such estimates play a role? Such estimates play a role when the B is kind of bad. So what do I mean with for instance, with a bad coefficient B? It would be kind of very singular if this really maps from V into H. Like if it would be the case that A is a second order operator, you could think of B as a first order operator or something like that, like was in the last talk, or this morning talk by Franco Flandoli. So this condition is somehow to make sure that you have enough of A to be able to somehow win over this term B. And I will not consider this condition for this general equation. I will now do a very special choice. And the very special choice I do is that I consider this linear equation. So let me copy that. I forgot to clean the blackboard. So let's copy this equation for the moment. So it's du plus, so I put the A on the left-hand side in order to have positive operators. And now the 2 is not a typo, dw. And there's some initial condition. Now, and here this will all be on a Hilbert space E. The whole talk most of the talk will be on a Hilbert space E. So there will not be any difficult Banach space stuff that I usually explain, but not this time. And A will be the generator of an analytic semigroup, and the B will be what I said before. It will be basically half of the operator A. So if A is a second order operator, B could be a first order operator. If A is a fourth order operator, then this could be a second order operator. Okay? And just to make it as easy as possible, I take a standard Brownian motion. Yeah, you could take more, you could take cylindrical, etc. But I want to make it as easy as possible to go as far as possible. Now, I don't think it makes much sense to take this full stochastic parabolicity condition for this very easy equation. I think it would be natural to somehow replace it just with alpha is 2 and f is 0, and you would get such a condition. I don't think you will actually win something for this very special equation if you allow the other generality. And well, if under certain condition A and B, for instance, they have to commute, then I usually interpret this stochastic parabolicity condition in a slightly different way. I usually interpret it as that A minus 2 times B squared generates an analytic semigroup. Well, such things you have to calculate with Ito's formula, why this is the right thing. But we have seen such things in many talks already. And the usual transformation one does, we also saw in Flandolie's talk and also in some other talks. Okay. Well, some of the history for such equations. So first of all, using variational methods, this has been done for the first time by Pardue and later by Krylov and Rozovsky. And the thing is, in this approach, you somehow have to take P is Q is 2, and A has to be something like self-adjoint. Well, you can take it more general, but you have to start from some point. Another method to somehow study such equations is you could somehow do transformations using Ito's formula, and this has been done by D'Aprato and co-authors in the 80s. And we somehow extended that to the Banach space setting, which works. And you need then Ito's formula and Banach spaces. And then you can allow P and Q. So if you study this equation now on this space, I will not do that, but if you would do that, then you could study it for every P and Q between 1 and infinity. That's possible. But the important thing is you will need that B generates a group, otherwise these transformations that one usually does do not work. So the transformation I mean is the following. The transformation that is used all the time is that you take the Brownian motion and you take this guy and you multiply this. I don't remember if there should be a minus or a plus here. And you introduce a new, the other way around. You introduce a new function, and this will satisfy another equation, and you can somehow remove the stochastic part out of your equation by such transformations. But as you see, I mean, you need Brownian motion in front of the B, so you somehow need a group generator, otherwise you cannot write that down. Now, another approach for such equations would be to apply maximal regularity techniques. Well, that has been done by D'Aprato and also in a different setting by Bosesniak. By D'Aprato in the case P is Q is 2, and by Bosesniak in the real interpolation scale. Well, you can also do it really with LP spaces without real interpolation spaces, and this has been done in the analytic approach of Krylov, but then he only studies second order operators, and his B in that situation can be fairly general, but it has to do something with a group also in that case. Yeah, and we extended the theory of Krylov to all values of LP and LQ. And then if you would push this to get similar results, well, if you do it with general functional analytic methods, if you try to prove existence and uniqueness for such equations, you will need that this norm of B is small. But if you have more structure, like in Krylov's work, then you could repeat his PDE arguments also to get his results for all P and Q. Now, the question of the title of the talk is, does the stochastic parabolicity condition depend on P? So somehow, what changes in this work if you would like more integrability, or different integrability? So what changes if you allow P to be different from 2? So as you can see in all these works, it somehow will play a role, because here you need something, and here as well. And here you even need more, because you need that it's very small. So what is going on there? What is going on there? that was our question. And well, before I go into that, let me repeat at least this method here together with this method here, because I really like that method, and we just invented that, and maybe you do not all know this. Lutzweiss talked a little bit about it, but he talked about some different things that we are doing now. And in 2010 I actually gave a full talk on this subject, but I need to repeat at least one slide about it. So if you want to study this equation with fixed point methods, then a starting point could be a maximal regularity estimate for such equations, and then just iteration, and then you get a well-posedness result. So what kind of maximal regularity estimate am I talking about? Well, something like this estimate over here. So when do you have such an estimate? Well, you can prove this was proved by Da Prato. His assumptions are stated slightly different, but they are equivalent to what I stated here. If the real interpolation space is the same as the fractional domain spaces of the operator, then the solution to such equations you win a lot of regularity, namely half of the regularity. And so you start in E and you win half of the regularity. And you have here L2 and here L2. Okay? So you win a bit. And you also have some result about continuous paths. So if you cannot work then in the space dA to the 1/2, but the optimal space will then be the space E, and you have such an estimate. You have such an estimate. Now, if I specialize what we proved just to this situation, then you could say we proved this. We proved that if you have this, then for all G in this space, so I changed the P into, or the 2 into P, and P can be any number bigger or equal than 2, and you get the same estimate, but then here with a P, and here with a P. Okay, so it's really the same type of thing, and the assumption is really the same. You could, maybe a first guess would be that this 2 has to be replaced by a P, but that's nonsense. That would not lead to anything useful. So this is the right assumption, and you get such a result. Well, if you then go to these paths, what do you get then? Then you get here's a typo, sorry for that. There should be the real interpolation space 1/2 minus 1/p, comma p. I forgot this extra parameter p. So you get a regularity estimate of the paths in this space. So if p is 2, then you get again the space E back. Okay? You get again the space E back. So you can win something by taking p larger. But it's still an optimal estimate somehow. And there's, connected to all this is an open question that is maybe not so well known. And yeah, so the proof is very different from the case p is 2 actually. You need to do all kinds of other things. The p is 2 case is somehow special. You have more techniques to work with, because you can apply Fubini to go on. Well, the same thing is true for E is LQ, but you need slightly different formulations then. But I will not go into that. And you can also allow cylindrical noise. That's not really a problem. So what is the open problem? The open problem that there still is if you now take a general A, it may be an analytic semigroup generator or not. You can choose for yourself. Does one always have that the solution U to this equation have continuous paths? And also, do you have such an estimate? Well, the estimate you will certainly get by closed graph theorem arguments. So the question is really, does U always have continuous paths if you start with a G in this space? If you start with a G in this space. This is really unknown, and I would expect that it's not true, that you do not always have this. But counterexamples will be pretty complicated, because you need an operator A which does not have this condition. And such operators A do not occur in nature a lot. But there are many examples known of such operators which are kind of academic. But so this is really a mathematical question. I mean, but it's still interesting, I think. So people have been working on slightly different questions. If you do not have here a g, which depends on time and omega, but if you just have a fixed operator, which may be kind of unbounded in a certain sense, or non-trace class, if you have such a thing, then there has been a work by Talagrand and some co-authors, I think there are 4 or 5 people on that paper, where they somehow show that sometimes you do not have continuous versions, but that's a different question. I'm now speaking about real martingales. I mean, this will give a real martingale, this GDW. It will be a continuous martingale, and you have an A here, so you can ask this question. Okay, so this is a summary of the talk. I will go again to this the stochastic parabolicity condition and the number P. I will present several things on this. So it will be a very special SPDE for which you somehow have a new behavior. And I also want to analyze what this assumption means and if it's really needed. So what is my very special PDE? Well, it's the same that I already wrote down, but now I will take also a very special A and B. So there will be a C, which satisfies this, skew joint, and the A will be a positive operator, which I built from C, and the B will be very strange if you look at it for the first time. It will be alpha times C plus beta times the absolute value of C. So you can always build the absolute value of an operator C, that's not a problem. Yeah, and then I study this equation.
What is WT here now?
WT will now be a standard Brownian motion in order one-dimensional in order to make it as easy as possible. Yeah. So the new behavior that I will explain is already playing a role for this equation. But you could allow more general. So examples you could think of are C is ddx, because that's such an operator, and then A would be minus the Laplacian. Or you could also take C to be the Schrödinger operator, and then you get A is the Laplacian squared. I mean, I'm not saying that this equation with this choice of C will happen in physics or whatever. I'm not a specialist in that. I just want to have a mathematical equation which somehow has a new behavior. But this first one is certainly occurring if you leave out this part in the Sakai equation. The other one, the second one, I don't know, but could imagine that some sort of noises in some applications will have a Laplacian here and a bi-Laplacian here, but okay. So what is again this classical stochastic parabolicity condition that you have in this variational method? It is this estimate here. This this is really the estimate in that assumption. So if you now rewrite it for this special choice, what happens? So I think I have that, yeah. So I just substituted the choice of B and the choice of A, and you get something like this. And this looks kind of ugly because you have these absolute values here. And there's, yeah. But if you think about spectral theory, then you can still calculate all these things, or you just take an example like these ones, and you can then still calculate all these things. And what you get is that you can just write this like this. Okay, it doesn't change the thing. And remember, the K2 and the K1 were some constants. Well, but now we can just see that this will only be satisfied if this holds. If this holds. It will only be satisfied if this holds. So you somehow have stochastic parabolicity for this equation if this number is less than 1. So you get alpha and beta that to satisfies this. Okay, so you might wonder, is that optimal? And that's what we thought about. So we somehow found a way with different methods of constructing a solution, which in which we got this condition. So not this condition. So I now replace this condition by a p-dependent condition, and the p-dependent condition is this. Oh, if you take p is 2, then you get the old condition back, so you get the usual stochastic parabolicity condition. And what we can show is that for any p between 1 and infinity, there exists a unique solution u, which is in exactly the right space. You get a strong solution. It's locally in time. It's locally in time. I did not think about global behavior in time. I didn't care so much about that. And you get regularity estimates locally in time again. The usual regularity estimates for parabolic equations. But the funny thing is that you get this condition here. And now, of course, there are two situations that you might want to specialize in. So this is the condition. And somehow two interesting cases are p is less than 2 and p is bigger than 2. Well, if p is bigger than 2, then this condition will be, well, it will be more strengthening because well, if beta is not 0, then this will not be true for very large p. But if you let p go to 1, if p goes to 1, then this term completely disappears. So then it doesn't really matter how large this beta is. You can just choose it as large as you want, and if you take p small enough and alpha squared less than a half, then this will be satisfied for some p close to 1, and you get some sort of well-posedness result for your equation. So that's somehow strange. So that shows that the stochastic parabolicity condition is not always optimal if you take this very peculiar equation. But it also shows you that if you want well-posedness in LP instead of L2, and you want P to be large, then you need more than the stochastic parabolicity condition. So that's somehow two new phenomena that you see in this. So of course that is a natural question to say, is this really optimal? And I will come back to that. So these things I already said in words. Yeah, and the last point is somehow an interesting one in the proof. This p-dependent condition is actually, it's not a parabolicity condition, it is an integrability condition. Well, you will say, yeah, sure, because it's LP omega. But somehow in the proof, you will see that there is no parabolicity condition needed for such equations. It's actually an integrability condition. Okay? So let's go to the proof. So this is the only slide that is quite technical. So let's go through it slowly. It's just well, one slide of how the proof more or less goes. And I only give now the argument for the case C is ddx on L2 of the torus. The other cases you have to do by spectral theory, but it's quite similar. So you write your solution in a Fourier as a Fourier sum, and each of the un satisfies this scalar equation. Well, that seems not too strange. I mean, you have here this b, and this b has this form, and if you take c to be ddx, then well, that should be this in the Fourier domain. But this scalar equation you can solve, it's no problem. The solution, this should be un, sorry for that. The solution un is given by this. That's easy to check with the complex version of Ito's formula if you want. So this is a bit funny because you get here this part and you have this part here. So this is somehow sort of a group part because there's the alpha, and the alpha c is somehow a group generator, but there's also the beta times the absolute value of n, and that's somehow not a group. That's very different from a group. Oh, and the bn is some sort of number. Now it even gets more technical, this slide. Sorry for that. So I need a constant, so I take this constant. And I need to introduce 3 types of functions. I will come back to them. But the important thing is that if you calculate the norm in dA, this is nothing else than dA because we're working with this setting, and A is just the Laplacian. So if you calculate this norm, then up to constants, you basically get this power, and then some sort of thing with some sort of sum with the initial condition. And in the exponential here, you will have something negative in principle, and you will have something in front which has something to do with the Laplacian. Well, the f will be 2 times gamma t, and gamma is this number here. So this gamma will be negative. This gamma will be negative as long as so gamma is negative as long as 2 alpha squared minus 2 beta squared is less than 1. And that's the case in our setting, because we actually have even that if we add 2p beta squared to it, we are still less than 1. So this number will be positive. Sorry, this should be positive. So gamma is positive if and only if you have that. So this you could call a parabolicity condition. I mean, here you see somehow the parabolicity happening. This is in this f part. Now the g term is a bit strange, but it's not really destroying things because, well, there's a square here. It's not really a difficult guy. The strangest guy here is the h term. So here in the exponential. So the h is somehow, we have this constant here in front, and we have Brownian motion here. So if you look carefully here, I mean, it's Brownian motion squared in the point t divided by t. So this is nothing else than a standard Gaussian, right? It's just a standard Gaussian. So we have a standard Gaussian squared with some factor in front, and then e to the power that. So now if you will look at the question, when is this norm, this random variable that you get, when is this in LP omega? Well, that will be if and only if, I mean, this part is fine, there's no problem, but it will be if and only if this guy is in LP omega, this guy over here. If you calculate the LP omega norm, you have to take p over 2 moments, so this 2 will disappear. And now you can check that this will be the case, and that's an easy calculation because this is a standard Gaussian squared with a constant in front, and you can calculate for which constant this is fine, and the constant you will get is this. It's exactly this. So it turns out that the LP omega well-poseness is just equivalent somehow to this condition. Well, this is just a sketch of the argument. I do not give all details, but this is more or less what's happening in the proof. Okay, so is it sharp? Is it sharp? Let's think about that. Well, if you in the previous proof I took this choice, and this choice it is really sharp, as we also basically saw in the proof, because I wrote here equivalence everywhere. So we know that this gives well-poseness. I already stated that in a theorem, and the reverse theorem is also true. So if this number is bigger than 1, then you can find initial values, actually a lot of initial values, for which you get a blow-up. So if you take such numbers and you take this deterministic initial value, just doesn't really matter what you choose, but this is one which you can easily calculate with. If you define this deterministic time tau, which is a positive number in this case, if you define this tau, then you have a blow-up in certain ways at the point tau. Yeah, at tau, the equation doesn't make sense anymore. The solution will blow up. So in that sense, it's sharp. And if you take different initial values, so if you take different powers here, then this number tau will change, and you can probably make it as small as you want, but that's not the point. So this p-dependent condition for well-posedness is really sharp. But I don't know if I would call it a parabolicity condition, because it's actually an integrability condition. Okay. Yeah, so that's what I want to say about this this result at the moment. There's one more ingredient in the proof that I need if p is less than 2. So if p is less than 2, I did not comment too much on it, but a fairly technical point is that we need a certain weak characterization of stochastic integrability in Hilbert spaces. So if you did not get what I was saying before, you can wake up again, because this is just some sort of intermezzo with some funny result about stochastic integration in Hilbert spaces that might be useful for you. So you can give a weak characterization. So we found some result in 2007 in a much more general context, but let me just state it now in the context of E being a Hilbert space. So you take a process which takes values in E, you have to make sure it's progressively measurable, and if you now assume that for all numbers of for all vectors E from E, you have that this is just a scalar product. This is somehow in the space LP omega with values in L2. Okay, that's a condition which might be easy to check or not. Well, if there exists a random variable psi in LP, and p is bigger than 1, but it has to be a random variable from omega with values in E, such that for all E, you have that this random variable and then the scalar product with E satisfies this identity. And what I wrote here is a stochastic integral of this phi against E. This exists because this is assumed to be in LP omega with values in L2. So this will exist by the Burkholder-Davis-Gundy inequalities, just scalar valued, as an LP random variable. And I'm not now asking that it is equal to this guy. Well, then you can already conclude that phi will be in this Bochner space LP omega with values in L2 with values in E. So some sort of, here you have something weak, and here something weak, and you have here you have something strong, but you can derive this, and you then also get that phi is stochastically integrable, and the stochastic integral will be equal to psi. Okay, so some sort of weak stochastic integrability gives this strong condition and this identity. Ah, sorry, yeah. So U and phi are the same in this this slide. Sorry for that. Yeah, I messed up the notation here. Yeah. So this is the same guy as this guy. Yeah.
Excuse me, psi must be FT adapted or something, because otherwise it is only the projection.
No, you don't need that psi is FT adapted. You get that automatically because psi is weakly equal to this random variable, and this random variable will be FT measurable. So you get it automatically.
The omega space would be larger. The equation of the omega.
Yeah, that doesn't matter. I mean, if you take a bad psi, which is say F infinity measurable instead of FT measurable, then because of this identity and the Pettis measurability theorem, you get that psi is FT measurable anyway. So you don't need that as an extra condition. Well, you might wonder if this is limited to the case p bigger than 1. And with Martin Ondriat, I thought about extending this result to the case p is 1, and that's possible. We extended it to p is 1, but you get a slightly less strong result. But still, you get this strong identity. But we also thought about a counterexample to this weak characterization, and we somehow found one. So if p is less than 1, then it doesn't work anymore. So that's good to know or bad to know. Depends how you look at it. So there exists a progressive measurable phi, which satisfies that it is in this space against these vectors E for all p between 0 and 1, so it is in this space for all p between 0 and 1. And weakly it will give a stochastic integral which is 0, okay? But still, this will be infinite, almost surely. This will be infinite, almost surely. So in particular, then you cannot integrate it, right? You cannot stochastically integrate it. So this theorem is really limited to p greater or equal than 1. Okay, so how did we use this? Well, we used this weak characterization in the proof for this equation, I mean, this kind of stuff, to get stochastic integrability, so some sort of trick. Now the LQ case you can also do. So you can study such equations also in LQ spaces. So that I will comment on now with 2 slides. So the first slide is nothing else than an explanation how to work with LQ norms if you are integrating functions with values in LQ spaces. So if E is LQ over some measure space S, then you can do as you do in the Hilbert space framework, just stochastic integration. You have 2-sided estimates, but somehow the thing you get, if you want to estimate this guy 2-sided, you get this type of norm. That was also in Lutz Weiss's talk. You get this type of norm. So this will somehow play the role of the usual space that you get in stochastic integration. So it's sometimes difficult to work with, but it's very explicit. I mean, this norm is completely explicit. So if you have some situation where you need LQ spaces, this is sometimes helpful. Yeah. Even if you want further results, if you want to work with L1, you can still do it, but you get some one-sided inequalities. Now the result I stated for this stochastic parabolicity condition and this well-posedness is also true in LQ spaces. So if you now take this special case, so this equation again with this special choice, but now on LQ, then you still get well-posedness if this condition holds. And you get then well-posedness in some sort of space like this. And if this condition doesn't hold, then you get the blow up again. So funny is that this will not depend on Q. I mean, this will not depend on the space you will work with. It does not depend on Q. Yeah, so the proof is very different from what I said previously, because it's more complicated, because you have no orthogonality now in LQ. So you need to use a multiplier theorem to be able to estimate such norms. But in principle, it's the same kind of argument. Krylov once commented on all these things that his student has found also some negative result. And what was the negative result? If you take A to be Laplacian squared, so just this equation, and B to be minus beta times Laplacian, so this will be the same thing as here, but there is no alpha term. Okay, so it's really the same situation. And why did I put a minus here? Because Laplacian is a negative operator, and the absolute value will be a positive operator, so I need the minus. So what happens is that the student found that some equations are not well posed in this space, and if he replaced this 4 by a 2, it was well posed. And they were somehow puzzled by what's going on there with the stochastic parabolicity condition. And with our framework, we can now explain what's going on. B does not generate a group, and you somehow get difficulty with stochastic parabolicity conditions. But what we do get is that we have well-posedness in all these spaces, even with P not equal to Q, as long as this holds. So you get well-posedness for this equation, but maybe not in this space. Maybe you have to change this exponent in order to get well-posedness. So I have some concluding remarks. if you have equations with this, then this is, say, the parabolicity condition, the stochastic parabolicity condition, you could say. But if you want well posed in an LP setting, then you get an extra condition, which will be an integrability condition. Of course, this only holds for our model problem. It's not clear what happens for other problems at the moment. Yeah, and what is also for me an important conclusion is that the LP theory of Krylov is very strong, but it's somehow limited to second order scalar equations. As soon as you leave that, if you go into fourth order equations, etc., then you will get into difficulty with these p-dependent parabolicity conditions, because what he has in his second order equations for the term b is basically something like ddx. So that makes that things are a group, and that makes it a bit better. So the groups are fine, as you can see, because the group part is here, the alpha is something with the group, and there's no p here. The p only happens somehow for the non-group part. So the same thing you would have if you replace second order scalar by systems. If you go to systems, you will get into similar trouble, because for systems you will also not have group generators. Okay, so this classical parabolicity condition can be improved in some situations where you have more structure. But of course, a good question would be what kind of general theory could you expect in this framework of variational approaches to SPDEs? What can you expect for LP theory there? That's somehow unclear. And also, what is unclear at the moment, what happens for p is 0 if you somehow do not want any integrability conditions. So if you let p go to 0 here, you will somehow get this condition. And that's somehow the right parabolicity condition that one would have. But it's somehow difficult to let p go to 0 for all kinds of reasons. Okay, so yeah, there might also be some connection with the talk of Lutz Weiss, but that's also unclear at the moment. Okay, thanks a lot for your attention. So here are some of the papers that my talk was about.
Thank you very much. Are there some questions or comments?
I didn't quite understand your that counterexample you showed with the p less than 1. How? Maybe I didn't. Yeah. So how can you make sure that that stochastic integral is 0?
Yeah, that's a strange phenomena, I agree. But that's actually possible. Yeah.
Yeah,
So
but how do you do it?
There's a funny construction of Dudley, and so Dudley showed that the representation theory if you take a psi, which is ft measurable, if you take a psi which is ft minus measurable, so slightly better, then there exists a phi which is in L0 omega L2, and it's progressive measurable, such that the stochastic integral of phi will be equal to psi. So Dudley extended the representation theorem, the well-known one, he extended it to an L0 setting. But the problem is, there is no uniqueness here. You do not have uniqueness here. But you can always find such a phi which will give this psi. So what you can then do is take, you can repeat this on the interval 1/2 to 1, so you can find a phi which gives Brownian motion at 1/2, maybe with a minus. And then, so you can find such a phi. And what you can then do is you define a new phi to be 1 on 0 1/2, and you define it to be phi on 0, on 1/2 1. So what you will then get is that your stochastic integral over the whole interval will be W1/2 minus W1/2, and that will be 0. Okay? But it's a really strange result that is kind of surprising at first sight. Yeah. So this is due to Dudley. And we somehow used Dudley's construction in a non-trivial way to construct a function phi which takes values in an infinite dimensional space, and to do this.
Okay, so morally it's a bit similar to when you rewrite the Brownian bridge as an SDE, and it sort of blows up at the end in order to force it.
Yes, exactly. So this phi will blow up at the end point, yeah. And in that way you can build strange things. Yeah, that's what's going on.
Okay, if there are no more questions or remarks, let's send the speaker again.